All right, this is the final lecture for Chapter 14. It will cover sections 4 through 6. Section 4 is about reactions of esters. Section 5 is on amines, and Section 6 is on amides. So Section 14.4 is hydrolysis of esters. Hydrolysis is the reverse of esterification. In it, esters react with water, hence hydra, to form a carboxylic acid and an alcohol. In the process of this reaction, as you can see, water is actually going to get broken down, where the one in black is going to add to the essentially what becomes the alcohol, and the part of it in red adds to the carbonyl, forming a carboxylic acid. So the name hydrolysis means to break down, or lyse means to break apart the water, which is exactly what we're doing here. We're breaking apart water to form a carboxylic acid and an alcohol, and obviously in the presence of an ester. All right, so what happens here, I'm going to move this to the side. If you look at the equation, I know it's really tiny, but it says H plus and heat. So this has to happen at high temperatures and in the presence of an acid. All right, so since we have an acid, I'm going to write the ester here as such. Okay, there's a lone pair on the carbonyl right there, and we've got this acid floating around, which means there's H pluses. Okay? So what's going to happen is, and there's lone pairs on the oxygen here. What's going to happen, it turns out, is the oxygen on the carbonyl, the one that's doubly bonded to the carbon, is going to attack that acidic proton. And so as a result, this is the first step. We get this intermediate. Okay? And the reason that can happen is because you have the partially negatively charged oxygen there. We have a partially negatively charged oxygen on that. But it's not going to happen on this portion, on that oxygen, because it just doesn't work. The one on the carbonyl, what can happen is that this double bond can overcome that negative charge by putting two of those pi electrons up there. And so this can then form this structure, essentially. Okay, so now we have a positive charge on that carbon. That's not actually like how it's going to exist at, but which would rather have a positive charge, a carbon atom or an oxygen atom? The answer is the carbon, because it's less electronegative than the oxygen. All right, so that's why it would happen there. If it happened at the other oxygen, there's no double bond right here to accommodate it, and it would have to break the bond for that, which a carbon-oxygen bond can't just break by itself. So essentially it has to happen at the carbonyl. All right, so this we're going to ignore though, because what's going to happen at the same time is, and let me kind of start this over, but here we go. All right, here. We have the water obviously floating around, and I'm going to make this blue and red. All right, so you've got this partially negatively charged oxygen atom, and that is going to attack the carbon right there, because as I showed, it can have a positive charge. It will, at the same time, do this, where that double bond can then freely move up there by itself. And so we get, as a result of this, we get an OH, we get your OCH3. Here's the oxygen from the water that is attacked. And you get that. Now you have a positive charge on the oxygen that came from the water. Well, we still have the lone pairs of the what now has become an ether. And they can attack the blue oxygen. I mean, I could have made the blue one over here. I just wasn't really thinking about that as I was drawing it. But essentially, they'll attack one of those hydrogens and make this. Positive charge will be there, and now we've got this, which is called a hemiacetal, essentially. All right, and then from there, either of the two oxygens, and actually this one should be red, okay? But based on the way the product has been shown, one of the two lone pairs on the black oxygen, that's an alcohol, can form a double bond right there, which kicks off ultimately methanol, and you get this right here, and methanol. Okay, and then once you take it out of the acidic solution, the proton there can leave, and you get acetic acid and methanol. So this is how the acid hydrolysis of esters work. You can see it needs to be done at high temperatures, and ultimately it says that the carboxylic acid is more stable in solution at high temperatures in an acidic solution than the corresponding ester. Example 6. What are the IUPAC and common names of the products from the acid hydrolysis of ethyl propanoate? So first of all, we have to draw ethyl propanoate. And that's going to be like this. We have our carbonyl. We've got our ester portion. Since it's ethyl propanoate, we draw 2 carbons off of there. And there must be 3 because it's propyl on the left. So 1, 2, and 3. So there's ethyl propanoate. And it's going to undergo acidic hydrolysis. All right, so as a result, what we're just going to do is basically kick this off, and we're going to get the carboxylic acid, and we're going to get ethanol. So we go from ethyl to ethanol, and then the compound here is propanoic acid. Because of that. We can also hydrolyze esters in the presence of base. Now this doesn't actually break down water because we're starting with a base, so we can see here sodium hydroxide. There's no water there, but because the acidic portion does break down water, it was called hydrolysis and made ultimately a carboxylic acid. And they noticed that if you reacted them with bases, you'd get essentially the same thing. So if we have these hydroxides floating around, there's HO minuses. that's just going to immediately attack the carbonyl. All right, like this, which will put those pi electrons up to that oxygen. So then you get an O minus here, you get an OH and an OCH3. That negative charge can just go down and kick off the methanol, essentially, and you get OCH3 minus. All right, and then at that point, it doesn't actually show this here. This is really what happens, and I guess that could take that hydrogen off of it, but you would work it up in the lab and you would add some acid to it, and that would ultimately make the acetic acid, because you'd have this, it would form acetic acid, and then your methanol would also be there. Okay, so with base hydrolysis of esters, you at the very end you add acid. With acid hydrolysis of esters, at the very end you'd add a base, because you might remember that you ended up with this positive charge there, and you'd have a base at the very end added to remove that, to just make it this. So example 7, draw the line angle formulas for the products from the hydrolysis of methyl benzoate with potassium hydroxide. So benzoate is going to look like this. And it's methyl, so we just have one right there. So this portion and that, here we go, the red is going to be from the benzoate part, and the blue is the methyl. So methyl benzoate is our ester. Potassium hydroxide is going to come in, so we have an OH minus. It's going to attack here, which will move up the electrons from the pi bond, which will then move down and kick off that, the ester portion of it, and you get the carboxylic acid right here, and you get methanol. So methanol will be one product, and benzoic acid would be the other. Now technically, this would be after you work up the reaction, so your book might say sodium benzoate and methanol, or it might be sodium methanoate and benzoic acid. I don't remember, I'm not looking at it right now, but either way, you're not going to actually get those salts as products. You're going to add an acid at the end of this to make both of these compounds neutral, so benzoic acid and methanol.